Assalamu alaikum warahmatullahi wabarakatuhu. So in this video we will be continuing our topic transformer. So in the previous lecture we have seen that all the approximations that we have made in the ideal transformer that can be put back into this circuit so that our analysis could be more accurate. So first of all, we have seen that the copper resistance for the primary side, we have inserted it with the resistance Rp because it does not change in the it does not contribute in the lagging of the current or but this is the leakage flux, and that leakage flux actually causes the lag in the current, and that the best approximation with this lagging component is the inductor. So we have put it with the XP, which is the primary side leakage inductive reactance, and then we have the resistance RS is the copper wire resistance on the secondary side, and similarly for the leakage flux on the secondary side we have X of S. Now this is known as the excitation branch. This is known as the excitation branch, and RC accumulates the losses in the form of hysteresis and eddy current losses, because they also do not contribute in any phase difference between the voltage and current. But we have this XM, which is the which is the mutual flux actually, and that is also causes the lag in the current. So we have modeled it with the inductive reactance XM. So this is actually required to set up the flux in the primary side, and that can be induced into the secondary side. So in the middle we have this ideal transformer. So now we can transform the impedance that we have seen earlier. How we can do it? So to remove the transformer and moving the transformer model refer to its primary voltage levels, and we have moved it everything to the primary side. So we can see that if we remember that relation, Z prime is equal to A square Z load. Now this is Rs and X square, X of S square, that will be acting as a load. If we go to this previous slide here, so we will be transforming impedance to the right side. Okay, so the turns ratio will be used as the transformation factor. So that is A square times R of S and A square times X of S. The rest of the part which are already on the primary side will not be changed. And also remember that excitation branch is only shown on the primary side because the excitation current is required only on the input side. It doesn't matter whether it is a high voltage side or the low voltage side. If it is a step up transformer, it will be on the it will be on the step up transformer high voltage side, and if it is a step down transformer, it will be on the low voltage side. So we can also transform the components to the secondary side, and all those components will be changed. So here this is equal to IP, that is why it is IS over A, and VP is equal to A times VS. So all the voltages are also transformed. Similarly, if we want to transform the impedance to the load side, so what will happen means if we have this one, so we transform the impedance to this secondary side. So what will happen? We can see that the opposite will be happening. So as we know that IS over IP is equal to A. Now I in terms of IS, because we are looking all the parameters in terms of the secondary side, so IS will be A times IP here, and then similarly that will be the opposite, RP over A square, XP over A square, RC over A square, XM over A square, and these will be the same values. So this is just the transformation of the impedance from one side of the transformer to the other side. So we can use if we are transforming to the primary side, so we can use this figure, and this top one figure that actually shows all the impedances transformed to the primary side, and the bottom figure shows that all the impedances are transformed toward the secondary side of the transformer. So sometimes this transformer model actually becomes more complex because of the addition of another node, and sometimes making circuit solution more complex. But there is an the good thing about this circuit is that the excitation current normally is about 2 to 3% of the full load current for the typical transformers, for power transformers. So we can actually make a more simplified equivalent circuit that can be modeled as or that will be modeled as the original one, and that can produce the results even means closer to the ones we have, but here we have uh, closer to this one actually. So how we can do that is that we can move the excitation branch in front of the transformer, and the primary and secondary impedances are left in series with each other. So obviously that will make it more easier to solve these circuit now. So in some applications, sometimes the excitation branch may be neglected entirely without causing serious error. So let's look at these figures. What happens if we just move them, uh, we just move this excitation branch in front. So because this is for the when we have transformed the impedance to the primary side, and this is for the when we have transformed the impedances to the secondary side. So we can see that here we have the R equivalent and JX equivalent. They are just the series components of resistances, RP plus A square RS, and similarly X equivalent P is XP plus A square XS. Similarly for this one, RP over A square plus RS, and XP over A square plus XS. So now it's more simplified circuit, and somehow it will produce the approximately same results that we can get from the real transformer. Similarly, if we are in a hurry, we can say that so we can even remove this excitation branch, because again, if we assume that this excitation current is very small, and as we know that it could be around 2 to 3% of the full load current, and full load current is very high, so we can even remove this branch to analyze this transformer. So it will be simply just a RL circuit. So in this video, we have seen that how we can reduce our circuit by putting all those approximations that we have made for the ideal transformer. That in ideal transformer, actually, we have assumed that there is no resistance for the primary and secondary windings. There is no leakage flux, and there is no other losses in the transformer. So we assume any all the lossless transformer. But here in this video, we have seen that how we can put all those together, and how we can simplify that circuit to analyze those transformers, so that we can reach up to approximately close to the actual results of the transformer. I hope you have understood in this video. So if you have any question, feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuhu.